Imagine you're standing outside on a clear night, looking up at the sky. You can see stars, thousands of them. And somewhere out there, past the moon, past Mars, past Jupiter and all its moons and all the swirling gas and ice and rock, there is the edge of our solar system. And here is a thought that keeps some people up at night. We've actually sent rockets out there, real rockets, built by human hands, launched from a little blue dot in the middle of nowhere. And they're crawling toward that edge right now, as you read this, as you breathe, as you blink. But here's the thing. Here's the thing nobody really talks about. Even those rockets, the fastest machines our civilization has ever built, are going to take tens of thousands of years to reach the nearest star. Not a few centuries, not a few millennia, tens of thousands of years. So what is actually going on? Why is space so impossibly hard to cross? And why can't we just build a bigger rocket and go faster? That's exactly what we're going to figure out today. And I promise you, by the end of this, the universe is going to feel both more terrifying and more wonderful than it did when you started. Let's begin with something you already understand. You understand distance. Maybe not cosmic distance, but everyday distance. You know how far it is from your house to the grocery store. You know roughly how long it takes to drive across your country. You have a gut feeling for distance. Good. Hold on to that, because we're about to stretch it until it snaps. The moon is about 384,000 kilometers away from Earth. That sounds like a lot. The Apollo astronauts took about 3 days to get there. 3 days of drifting through black emptiness to cover that gap. Now, Mars at its closest to us is about 55 million kilometers away. That's roughly 144 times farther than the moon. A trip to Mars, with current technology, would take somewhere between 6 and 9 months. Not days. Months. And Mars is our neighbor. Mars is basically next door in solar system terms. Now here's where it starts to get genuinely strange. The edge of our solar system. This fuzzy, uncertain boundary where the sun's influence starts to fade and interstellar space begins, is roughly 100 to 150 times farther than the distance from Earth to the sun. The sun is already 150 million kilometers from us. So we're talking about distances that start to make ordinary numbers feel silly. And the nearest star to our sun, a small red star called Proxima Centauri, sits about 4.2 light years away. 4.2 light years. A light year is the distance light travels in 1 full year, and light moves at about 300,000 kilometers per second. In 1 second, light crosses a distance 7.5 times around the entire Earth. In 1 year, it travels about 9.5 trillion kilometers, and Proxima Centauri is 4.2 of those years away. Let me give you a way to feel that. Imagine you shrank the solar system down so the sun was the size of a grapefruit sitting on a table in front of you. On that scale, Earth would be a tiny grain of sand about a meter away from the grapefruit. The outermost planets, Neptune and beyond, would be maybe 40 meters away, still in the same room or just outside the door. The edge of the solar system's influence, where the sun's magnetic bubble starts to thin out, would be about 100 meters away, and Proxima Centauri, the nearest star, on that same scale, it would be sitting somewhere around 270 kilometers away, in another city. That is the scale of the emptiness we're dealing with. And our rockets, our Voyager probes, our fastest spacecraft, are like dust specks drifting across that 270-kilometer gap at the speed of a bicycle. Now you might be thinking, okay, so we just need faster rockets. And that's a perfectly reasonable thought. But here's where the real puzzle starts. Let's talk about what a rocket actually is, and why making it go faster isn't as simple as putting in more fuel. A rocket works on a beautifully simple idea. You throw stuff out the back, and the rocket goes forward. That's it. Isaac Newton figured this out centuries ago. Every action has an equal and opposite reaction. You push gas backward, you push yourself forward. Simple, elegant. Works in the vacuum of space where there's no air to push against, because you're not pushing against anything outside the rocket. You're pushing against your own exhaust. The rocket carries its fuel, burns it, throws the hot gas out the back, and moves forward. Here's the problem. To go faster, you need more thrust. To get more thrust, you need to burn more fuel. But to carry more fuel, you need a bigger rocket, and a bigger rocket is heavier, And a heavier rocket needs even more fuel to accelerate. And more fuel means more weight. And more weight means more fuel. And more fuel means more weight. This goes around and around in a circle that gets vicious very quickly. Engineers call this the tyranny of the rocket equation. It's not a joke. It's a genuine constraint baked into the physics of how rockets work. The math was worked out by a Russian schoolteacher named Konstantin Tsiolkovsky back in the 1800s, and it's both beautiful and brutal. It tells you exactly how much velocity your rocket can gain based on how much fuel it has relative to the weight of the rocket itself. And it does this with an exponential relationship, which is the mathematical way of saying things get ridiculous very fast. Here's a concrete example to make this real. The Saturn V rocket, the machine that carried humans to the moon, was one of the most powerful machines ever built. It weighed about 2.8 million kilograms, fully loaded on the launch pad. By the time it finished doing its job and the tiny capsule was cruising toward the moon, only a few thousand kilograms remained. Almost all of that enormous machine, most of its mass, was propellant. Fuel and oxidizer to burn that fuel. And the speed it achieved to get to the moon was about 11 kilometers per second. That's fast. That's actually extraordinarily fast by everyday standards. But the nearest star, to reach Proxima Centauri in a reasonable human lifetime, say a century or two, you'd need to travel at something like a tenth of the speed of light. That's 30,000 kilometers per second. The Saturn V got to 11. You need 30,000. Now think about what the rocket equation says you'd need to multiply your fuel load to go that much faster. The numbers become completely absurd. You'd need a rocket with more mass and fuel than exists in the observable universe many times over. It's not that we haven't built a good enough rocket yet. It's that the rocket design itself, the fundamental concept of carrying your fuel with you and throwing it out the back, mathematically cannot get you to even a small fraction of the speed needed for interstellar travel in any reasonable time frame. The physics is doing something extremely rude here. It's not saying the goal is difficult. It's saying the approach is fundamentally broken for those distances. So let's step back and ask a different question. How do we go fast in space at all? Because our actual spacecraft, the ones we've launched, are going at incredible speeds relative to things we can imagine. And they got there through a trick, a beautiful trick called the gravity assist, or the gravitational slingshot. And understanding this trick tells you a lot about how clever humans have been about working around the tyranny of the rocket equation. Here's how the slingshot works. Imagine you're rolling a ball toward a moving car. If the car is moving toward you and you throw the ball at it, the ball bounces back faster than you threw it. Energy got transferred from the car to the ball. Now do that with a spacecraft and a planet. A spacecraft comes swooping in toward a planet from behind, in the direction the planet is moving around the sun. The planet's gravity grabs the spacecraft, swings it around, and flings it forward. The spacecraft effectively steals a tiny, incredibly tiny, essentially unmeasurable bit of the planet's orbital energy. The planet slows down by an amount so small you'd need instruments beyond anything we have to measure it. The spacecraft speeds up by a significant amount. Free velocity, no fuel burn. It sounds like cheating, and it sort of is, in the best way. This is exactly how we got our Voyager spacecraft to reach the outer planets and eventually escape the solar system. Voyager 1 and Voyager 2, launched in 1977, used a rare planetary alignment to slingshot around Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune as well, gaining speed at each encounter. Voyager 1 is currently the most distant human-made object in existence. It's about 23 billion kilometers from the Sun, give or take. It took 46 years to get there, and if it were heading toward Proxima Centauri, which it isn't, it would take roughly 73,000 years to arrive. 73,000 years. Agriculture was invented about 10,000 years ago. So Voyager, our fastest long-distance traveler, moving at about 17 kilometers per second, would need 7 times the entire span of recorded human civilization to reach the nearest star. This is why the phrase "rockets can't escape the solar system" in any meaningful sense is genuinely true, even though technically we have done exactly that. Voyager has escaped. It crossed the heliopause, the boundary of the sun's magnetic influence, back in 2012. But escaping the solar system's gravitational grip entirely, actually getting somewhere else, reaching another star, is a completely different thing. It's like saying you escaped your house, but you're still in your neighborhood, your city, your country, your continent. The solar system isn't even a neighborhood on the cosmic scale. It's a doorstep. Let's go even deeper because there's another layer to this problem that most people never hear about. Even if we could somehow magically solve the rocket fuel problem, even if we had an engine that could push us to a significant fraction of the speed of light, there's another wall waiting for us. The universe imposes a speed limit, and it is absolute, and it has never been broken, and there are very good reasons to believe it cannot be broken. The speed of light in a vacuum, approximately 299,797 kilometers per second. Nothing with mass can reach it. Not approach it without consequences, not sneak past it, not go around it. It is a hard ceiling built into the structure of reality itself. Now why? Why does this limit exist? Einstein figured this out in 1905, and the answer is strange and beautiful and takes some getting used to. The short version is this. Energy and mass are the same thing, seen from different angles. Mass is a kind of frozen energy. When you accelerate something, you're adding energy to it. But as you add energy, the object's effective mass increases. The faster something goes, the more energy you pour in, and the more that energy goes into increasing the mass instead of increasing the speed. As you approach the speed of light, it takes more and more energy to go just a little bit faster. As you get very close to the speed of light, it would take infinite energy to get there. The speed of light is not a wall you crash into. It's a horizon that retreats as you approach it. You can get closer and closer, burning more and more energy, but you never arrive. And here's where it gets genuinely mind-bending. Time itself is part of the picture. If you could travel at, say, 90% of the speed of light, time for you would actually slow down relative to people back home. You'd experience less time passing. At 99% of light speed, your clock would tick about 7 times slower than the clock on Earth. At 99.9%, about 22 times slower. This is called time dilation. It's not a quirk or an error. It's been measured. GPS satellites have to account for it, or your phone's navigation would drift off by kilometers every single day. Time really does pass differently depending on how fast you're moving. And while this might sound like a useful trick for interstellar travel, it doesn't actually solve the energy problem. Getting to 99.9% of light speed still requires energy beyond anything our civilization currently produces, by orders of magnitude that are difficult to even express in normal language. So here we are, trapped by the rocket equation, limited by the speed of light, sitting on a tiny rock in the middle of incomprehensible emptiness. Does this mean we're stuck here forever? Does it mean we'll never go anywhere else? That's the question that haunts physicists and engineers and dreamers, and it's a question that has some genuinely interesting possible answers. Not solutions we have, but ideas that are being seriously explored. Ideas that make you realize humans are not done being clever about this. One of the most fascinating proposals is the concept of a solar sail. Instead of carrying fuel at all, you use the pressure of light itself to push you. Light has momentum. Even though photons, the particles of light, have no mass, they carry energy, and that energy can push things. A large, incredibly thin mirror in space would feel a constant, gentle push from sunlight. No fuel, no exhaust, just the continuous pressure of photons bouncing off a surface. The push is tiny, ridiculously small, but in space, where there's nothing slowing you down, even a tiny, constant push adds up over time. In theory, if you started with a very large, very thin sail, you could keep accelerating for years and eventually reach a good fraction of the speed of light. There's a project called Breakthrough Starshot that's actually planning a version of this. Not with sunlight, because sunlight isn't intense enough, but with a powerful laser beam aimed at a tiny chip-sized spacecraft with a sail only a few meters across. The idea is to accelerate these tiny probes to about 20% of the speed of light and send them toward Proxima Centauri. At that speed, they'd arrive in about 20 years. They'd be too small to carry much. They couldn't stop once they got there. They'd just fly past. But they could photograph the system, study the star, maybe even get a look at the planet orbiting Proxima Centauri, a planet that might be in the habitable zone, a planet that might have water, a planet that might, in some form we haven't yet imagined, have life. And they'd send those images back at the speed of light, which would take about 4 years to reach us. So roughly 24 years from launch to data return. That's within a human lifetime. That's not a crazy timescale. The engineering challenges are insane, to put it mildly. But the physics works. There are wilder ideas, too. Antimatter rockets, where you annihilate matter and antimatter to release energy with 100% efficiency, compared to the fraction of a percent you get from chemical rockets. The problem is that antimatter is the most expensive substance in the universe to produce. If we gathered all the antimatter ever created in particle accelerators, we'd have perhaps a few nanograms. A nanogram is a billionth of a gram. You'd need tons of the stuff for a useful spacecraft, but the physics says it would work if you could make it. There's something called a nuclear pulse drive, which is essentially detonating nuclear bombs behind your spacecraft to push it forward. This was seriously studied in the 1950s and 60s under a project called Orion. It would work. It would be dangerous in ways that are difficult to overstate, but it would work, and it could in principle push a large spacecraft to maybe 3 to 5% of the speed of light. And then there are the truly exotic ideas, things that sit on the edge between science and speculation. Alcubierre drives, which exploit potential loopholes in general relativity to warp space itself, compressing it ahead of you and expanding it behind. So the space you're sitting in moves rather than you moving through space. If this worked, you could travel faster than light relative to the distant universe without ever locally exceeding the speed of light. Einstein's equations don't technically forbid it, but it requires something called exotic matter with negative energy density. And we have no idea if such stuff can exist in useful quantities. And the energy requirements calculated so far would make the antimatter problem look trivial. Wormholes. Shortcuts through the fabric of space-time. Again, not forbidden by the equations, at least not obviously, but to keep one open and traversable, you'd again need exotic matter. And creating one in the first place would require understanding of physics we simply don't have yet. These are not solutions. They're tantalizing hints that the universe might have loopholes we haven't found the keys to yet. But here's what I want you to take away from all of this, because I don't want you to walk away feeling hopeless or trapped. I want you to feel what I feel when I think about this, which is a kind of electric wonder. 100 years ago, humans had never left the ground in anything more powerful than a propeller plane. 60 years ago, we sent a person to the moon. 50 years ago, we launched probes that have now left the solar system. We are a species in our infancy when it comes to space travel. We have been poking at this problem for literally one human lifetime. The problems we face are not problems of will or imagination. They are problems of physics and engineering, and those are exactly the kinds of problems humans are extraordinarily good at solving when we decide they matter enough. The constraints are real. The distances are real. The speed of light is real. The rocket equation is real. But so is the laser, so is the solar sail, so is the fact that there are planets orbiting other stars, confirmed, detected, with instruments that didn't exist 30 years ago. So is the fact that there is a planet orbiting Proxima Centauri, the nearest star, a planet in the zone where liquid water is possible. So is the fact that there are people alive today designing spacecraft to send to that star. When Voyager 1 crossed the heliopause in 2012, the boundary between our solar system and interstellar space, there was a moment that scientists described as profound. For the first time in the history of life on Earth, a human-made object was floating free in the space between the stars, not orbiting the sun, not falling toward anything, just drifting in the vast dark between islands of light. That object was built from metal and silicon and wires, put together by human hands, launched on a column of fire, guided by mathematics worked out on paper in early computers. And it is out there right now, as you read this, a bottle with a message inside, drifting in the dark ocean between stars. The reason rockets can't simply escape the solar system and go somewhere in any time frame that matters to human beings isn't a failure of technology. It's the universe telling us something important about its scale, about the rules it operates by, about what it actually takes to cross the distances between stars. And the beautiful, infuriating, wonderful truth is that understanding those rules is the first step to finding ways around them. Every generation of humans has stood in front of a horizon and believed, for perfectly good reasons, that the other side was unreachable. And every generation has been wrong about that. The ocean was uncrossable. The sound barrier was unbreakable. The speed of light was just a number until Einstein explained why it was a speed limit, and not just a speed. We are not at the end of the story. We are somewhere in the very early pages barely past the table of contents. The solar system is not a cage. It is a launching pad, and we are, as a civilization, just beginning to figure out how to use it. Next time you look up at the night sky and see a star, any star, I want you to feel both the weight of that distance and the lightness of the fact that we already know it's there. We already have probes heading toward the edge of home, and we already had people figuring out how to close that gap. The universe is enormous, but so is the human drive to understand it. And that, when you think about it carefully, is the most remarkable thing in it.